Hey, Mr. McLeod here. Just want to talk about the beginnings of our unit on fluids. Primarily, I'm going to discuss density, pressure, the connection between density and pressure, a little bit of Archimedes' principle. I think I'll leave it at that. I think the next video, will deal with things like Bernoulli's principle, specific weight, or specific weight, things like that, or specific gravity. It's an interchangeable term. Anyway, so I know you are fully capable of looking up these formulas, and you potentially know how they can interact pretty easily just by changing up variables. But basically, I'm going to walk through kind of the nuances of it, basic ideas, the physics, right? All right, so let's start from scratch. Pressure. Pressure is defined as the force applied over a two-dimensional area, which this always begs the question, well, why does it have to be two-dimensional? Why can't we say a volume? Why can't pressure be a volumetric thing? And it's because when we're dealing with pressure, we're usually talking about pressure on the surface of an object. So even if we had a sphere, let's say we submerged a sphere into this beaker of water here, the actual pressure from the water would be on the surface of that sphere, and so we'd be more interested in what the surface area is of that sphere than the actual internal volume of it. So we only care about the walls of an object when it is under pressure. Okay, a really quick example of that. I'll draw you a three-dimensional rectangle here, also known as a parallelepiped or a, what's the term? I don't know. Parallelepiped is the actual technical term for it, but some people use other ones. All right, so let's say the base of this has a width of 2 meters. We have a depth of 3 meters and a height of 4 meters, and it is equal on all sides, despite my drawing looking otherwise. And let's say, just to make life easier at this moment, that we have pulled a vacuum on the inside of this parallelepiped, on this rectangle, three-dimensional rectangle. So we pulled everything out. There is no pressure from the inside pushing out. And so what we're going to have is a unequal pressure on the outside. If we think of Newton's third laws and we think of forces, we can imagine that there are force arrows pushing against surfaces, force vectors, but no force vectors in repulsion. So the material itself is either holding up to that force or this box would collapse. Let's say for a moment that the actual pressure we're dealing with is atmospheric pressure, which we often label as ATM, PATM. By the way, pressure is capital P, not a lowercase p. Lowercase p gets confused a little bit with rho, which is what we're going to be using for density. So we'll come back to rho here in a moment though. So just remember, capital P. Okay, now typically in the United States, when we deal with pressure, we like to call pounds per square inch, PSI. And atmospheric pressure at sea level, here in the Tri-Cities we're a little above that, so it's not quite right for here, but in general at sea level it is about 14.7 PSI. And if you think about it, PSI just means pounds per inches squared, pounds per square inch, right? And so this unit actually matches what we have here, force per two-dimensional area, pounds per square inch. But as you can already recognize, this isn't in metrics. This is very useful for us to think about so we can get an understanding of how much force we have, but it's not good for physics. So for physics, we're going to switch to the Pascal, and there is 101,000 approximately. These aren't actually zeros. If you get the actual value, it's a little longer, but we like to round it to 101,000. It's 101,000 pascals, PA, which is the same thing as saying 101,000 newtons per square meter. So you can see the unit once again matches force per area. So if you wanted to, instead of saying 101,000 pascals, you could say 101,000 newtons per 1 meter squared. And you get this, it would mean the same thing. So SI unit, pascals. Okay, oftentimes to simplify things, someone might write this as kilopascals. So what they do is they move the 0 3 times over. As you know from being in, having been in AP Physics 1, we want to be in the base SI units, so that way we're not having, because if you did it in kilopascals and then you had to use pascals to, let's say, solve Bernoulli's equation, you would have to go backwards and then convert it right back into pascals. And so oftentimes it's just written as 1.01 times 10 to the 5th pascals. And that is atmospheric pressure at sea level. Some of the homework problems you get doesn't use the Earth, it uses like imaginary planets. It uses planets with gases that have methane or propane or whatever else. And we'll get in more into that, changing this out. But just for Earth, this is this. When we launch our weather balloon, this is where it starts, and pressure goes down as it goes up, which is why, remember, our balloon expanded until bursting as it got higher in the atmosphere, because these force arrows decrease and the force arrows on the inside stay the same. Anyway, back to our drawing, now that I've got that out of the way. Okay, let's find the total surface area pressure on this parallelepiped. Rectangular prism, that's the word I was thinking of. It's also known as rectangular prism, parallelepiped's the technical name. But anyway, so as you know, if we find the area of this face, we just multiply it by 4 to get the area of all faces that are that are in the same plane, I guess, all the way around, and then we'll get the top and bottom face. So 4 times 2 is 8. 1, 2, 3, there are 4 sides with an area of 8. So we get 32 meters squared for this, and then the top and the bottom, this is 3 by 2, so 6, but you double it because there's a top and a bottom. So 3 times 2 is 6, 12, so we get plus 12, which is 44 square meters. 44 square meters is the area of our rectangular prism here, right? Okay, now, if this was a vacuum, if I pulled all the air out, if I, as you may see me do later this year, if I filled it with some water, boiled all the water out until it all became steam, and then supercooled it so that little bit of water vapor became, so basically if I created a vacuum in here, there's a whole method behind doing that, how much force would we have on the entire thing? So, if you look at our formula, pressure equals force divided by area. If we move area to this side of the formula, we just need to multiply area times pressure, and that'll give us the force over the entire object. So it's literally 1.01 times 10 to the 5th times 44. And like I said, this isn't going to be a number that we probably would have a real world understanding of. So in a moment, I'm also going to use the American system, the 14.7. So in pascals, 44 times 1.01 times 10 to the 5th gives us about 4,444,000 pascals, or 4 megapascals if you want to convert into with prefixes. Going back, let's look at what that is in PSI. 14.7 times 44, and it gives us 646.8 PSI. So that is a little under 700. Oh, as you were, I can't use this. This is in meters, right? So we would actually have to convert these to inches first. See, I made a mistake. Day 1 on a video, already making mistakes. So I'm going to convert this into feet. 4 times 3.28 plus or times 2 times 3.28 times 12, because they both need to be in inches, times 1, 2, 3, 4. There we go, this is starting to look more like it. Plus, because this is meters, this is a huge box, plus 3 times 3.28 times 2 times 3.28 gives us a grand total of 4,195 square inches over the entire surface. If you want to, you can check my math. That could be wrong. I just did it really quickly. Times 14.7. So it is a couple more steps if you want to convert it to the American system, because you can't use meters. You got to use square inches for PSI, pounds per inch, to work. 14.7. There we go. That's what I'm looking for. It's actually 60. This is a lot bigger. 61,678 pounds of force on this cube. And this is why when I have a little 1.5 meter by 0.5 meter steel drum, this is steel welded that's meant for oil and stuff, and I pull a vacuum on it, the atmosphere around it instantly crushes it like the fist of the Hulk, just using the air around us. And so this kind of leads us to this idea that we live in an ocean of air. It is easier to think of it as an ocean than it is to think of it as just a idle gas. In chemistry, we think of it as more of a gas. Physics, more like an ocean. And the reason is the deeper you are in that ocean, the more pressure you feel all around you. So if me standing here, 99.9999% of the atmosphere is stacked on top of me going about 22 miles up. And it is all stacked and it's all pushing on every part of me equally at 22 miles of air is stacked on top of me. And it pushes from all sides simultaneously. That's one of those rules of fluids. If you're submerged in a fluid, you get pushed on by all sides equally, and that's just because there's no room for anything to move. And we'll do some proofs of that later on. But basically, as we go further and further up in the atmosphere, as we raise our elevation, there's less air stacked on top of me. And like I said, you can think of it like the ocean. As you go deeper in the ocean, there is more pressure due to the water on all sides, and as you get to the surface of the ocean, there is less pressure. An interesting phenomenon, which we're going to talk about here in a moment, is if I go 6 feet down in the ocean, let's say 6 feet in a lake, let's stay away from salt water, because salt water is a little different. If I go 6 feet down in a lake of fresh water, and then I go 6 feet down in a swimming pool, even though the lake is so much larger than the swimming pool, the pressure I feel at that same depth stays the same. So this is one of those general rules, is the depth you are in a fluid affects how much pressure you feel or how much pressure you have on you. The shape of the container has zero effect on it, and that's because the forces are balanced on all sides equally. And so we can have a container that is straight vertical, or we can have a massive swimming pool, or we could even have, I'm going to erase some of this here. We can even have a zigzagging container. We can go like this, and like this, and like this. And as long as, and let's say we sit here, let's say this is full of water. We check the pressure here, here, and here in these fluids. We're going to find that they're the same in every single situation. And this should be familiar with you. Just because you are in a tall, skinny building, or if you are standing outside on the street, the pressure should feel the same, minus any air conditioners and stuff like that. But the air pressure, the fluid pressure due to the air, should feel the same no matter what the shape is of the container you're standing in. This is true for water as well. The shape of the container has no effect on pressure. So if you have a 20-foot straw and you are trying to suck up water through a 20-foot straw, and you were then to try and suck up water or try to remove water at the bottom of a 20-foot pool, you would find that the pressures at the bottom of the 20-foot straw were the same as the pressures at the bottom of the 20-foot pool. It's very interesting that the amount of water doesn't actually affect or the amount of fluid doesn't actually affect the pressure. And that's because there's a lot of cancellations going on. And this always leads to the question like, well, why aren't our bodies imploding? Why aren't we being crushed? Well, we have lungs, bones, muscular systems, everything that has evolved and changed over time to basically make it so we survive in the environment that we live in. And so we have 14.7 pounds per square inch of air on us at all times. So if you add up every inch of your body, you would get some very large number. You would find that the inside of your body is pushing out with the exact same amount of pressure, making us, as you know, in physics, in equilibrium. Okay, let's talk about density now, and then we're going to connect the two. Density. You watch Back to the Future. Marty McFly's father says, "I am your density," to his future wife in the movie, right? I thought that was one of the funniest things, even though just nerdy. Anyway, density, instead of big P, is rho. Little sideways, curly looking Q, or little P. Looks almost like a Q, but it's wrong. It's rho, it's a Greek letter. And it is based on, well, it's pretty simple. It's actually a really, just like pressure was pretty simple, this one's also pretty simple. It is the mass of something per its volume. It's never dealing with 3 dimensions, right? So how much mass it has, how much volume it has. Okay, going to units here, that's kilograms per cubic meter is the most common unit for that. And some, it's actually really useful. Let me show you why. So let's say, for instance, I have this little mass here. This little mass has a volume of, looking for my meter stick here. I look like I'm going crazy. There it is. Okay, I'm gonna estimate its volume by just looking at my meter stick here. So it has, and it's a cube, so once I find one side, I get them all. So 25 to 28, so it's 3 by 3 by 3 centimeters, which, as we all know, is 0.03 meters. So 0.03 cubed will give me the volume, which gives me a volume of, whoo, well, that's what it is. Gives me a volume of 2.7 times 10 to the, sorry about this, 10 to the negative 5th power meters, cubic meters. That's why this number's so big. And its mass is something else. I have a scale over here. I'll be right back. You're going to see why this is useful here in a moment. So, mass, triple beam balance. The scales are currently away, and yeah, triple beam balance is fun anyway. If the thing actually works, it may not actually work. Okay, this one's broken. Didn't know that. All right, let's get a good one. There we go. This is a better one. This one actually seems to do what it's supposed to. Yeah, I think you actually see this one on camera a little better as well. Okay, so triple beam balance here. Put it to 0 because right now it's all over the place. I zeroed it not too long ago, so it might still be zeroed. It's close, still a little off though. And good, close enough. All right, then we get the mass of this block. Drop it on there. Okay, it's more than 100. more than 200, less than 300. 250, 70, so less than 270, 271. I'm just going to estimate because I don't feel like that's super accurate. So it's 0.271 271 kilograms. All right, and if we divide these together, we should get our density. And then if I go and look at a density chart, I should be able to figure out what, in fact, this is made out of. This is one way of doing it. We're going to do the Archimedes principle a little bit sooner, and that you'll find that that's a little bit easier to do than this. So 2.271 divided by 0.527. I feel like I did something wrong here. What did I do wrong? Okay, and so now what I'm going to do is I'm going to quickly look at a density metal chart. Density of metals. Oh, I get it. It's usually in grams per cubic centimeter. I was like, these numbers are enormous. But physics, you know, we like to not do it that way. This is, oh, there it is. So the closest one we have, so I got an answer of 100,370 kilograms per cubic meter. Which means I did something wrong. It should actually be 10,037. So that means it's probably lead. Let's see, does this feel like lead? It looks like brass. Let's compare it. There's some other metals in here as well. This one's very low density. So you can see this method of weighing, getting the mass this way and getting this isn't the most effective. And the scale is not the most effective either, right? So Archimedes' principle is a little bit nicer when it comes to this. This was, once again, was 0.271. And once again, this was 3 centimeters. So let's try it in centimeters here. So let's try doing this in centimeters. So that'll be 271 grams per. So I said it was 0.0. So it's 3 cubed. 27. I don't know why I needed to type that in. So it's 27 cubic centimeters. Okay, I did something wrong, obviously, in my cubing on that previous number. So we're going to do it in gram and centimeters first, just to make life a little easier. Divided by 27 gives me 271. Gives me about 10.037. So we are getting the same value as we got previously. And let's see, what does it tell me? It's telling me the website's not safe. Hold on. Okay, it tells me we are between, it says we're between copper and silver. Okay, well, if we're between copper and silver, then I can make a pretty decent estimate that that thing is made out of brass. Brass being made out of copper and zinc. Let's see, density of brass. Let's look at that one specifically. Okay, density of 10 grams per centimeter cubed. Okay, so it's not a perfect thing. So my guess is it is a slightly heavier brass. And so using this method, we'll keep this in our minds. We have a density of, so this is density, let's call it 1, is approximately 10.0377 grams per centimeters cubed. Now keep in mind that this is the same as 10,037 if we're using the SI units, kilograms. But most of the charts online, they keep everything in grams per centimeters cubed. Physics, as you know, we like to keep things in kilograms. But I'm gonna use that for now just so it's easier to find it in charts and stuff. Okay, so that's that method. Let's move on for this real quick. And I'll leave this up here. And we'll get to Archimedes' principle here in a bit, and we'll try to use that as a comparative method. All right, so what else can we do? Well, we can combine, so far we have two formulas, right? We have pressure is equal to force per area. We have rho, which is density, is equal to mass per volume. And then we're going to get a second density formula. But this density formula is going to relate, second pressure formula. This pressure is going to relate density to pressure. And this has to do specifically with atmospheric or underwater pressure, or basically pressure in any fluid, is going to be rho. So we're starting right out with that density. G, gravity, H. Okay, this looks probably familiar to you as the gravitational potential energy formula. It's not the same because we're not actually looking at energy, we're looking at an actual measurable property of something. So it's a little different than energy, but it is rho G H. Meaning if you know the density of the fluid, you know the gravity of whatever planet or object that you're on, the depth within that object will give you that amount. So if we were to then say, let's say we're on Earth in the atmosphere. So here's Earth. This is actually one of the questions I gave you in your homework assignment. Is it says, okay, if I give you the radius of the Earth, you find the surface area. Gives you the formula for surface areas of a sphere. It's not the volume of a sphere, not the area of a circle. It's a different formula. But once you get the surface area of the Earth, okay, it asks how much pressure does the entire Earth have on it from the atmosphere. And so G is obviously going to be 9.81. Height is going to be the depth of the atmosphere. They give that number to you as well. And you're just going to find the surface area. And you're going to find the pressure on the entire planet, Earth. Finding the pressure for an individual object, you can do that as well. Now, if you look really carefully, if you look closely at this formula, once again, it does not give you the area of the object, right? It doesn't give you the area or the volume. Now you could make the argument, well, volume's up here in this formula. So if I increase volume, isn't it going to end up changing our pressure on that object? Well, no, because as you increase volume, mass is going to increase at the same ratio, at the same amount, not the exact amount, but the same ratio. And so rho is going to be a constant for any material made out of the same object. So you could have a small object or something even as large as, the surface of the Earth, like we were saying, and you're going to find that the pressure is going to be the same everywhere. So what should you get for the pressure all over the Earth? Well, you should get 14.7 or something around that, or if we're dealing with metrics, 101,000 pascals about at sea level. Once again, just like any other physics formula, you can plug in this formula for there. So you could also have force over area is equal to rho GH. And this gives you a lot of power to be able to start working with forces. Okay, I think another problem I gave you within the work asks for how much force does an object have that's submerged in a liquid at a certain depth. And then it gives you enough information. It gives you it gives you acceleration due to gravity, it gives you the density of the fluid, and then they give you the depth of the others. They pretty much give you everything you're going to plug into here. So it's a lot of plug and chug, but mostly it just wants to make sure you can combine these formulas into meaningful approximations. Yeah. So these are kind of the only three main formulas in this one derivation down here, or not derivation, a combination down here that we use for this first section. The next part we're going to move into is Bernoulli's principle and the Bernoulli equation. The Bernoulli equation is kind of the energy formula of fluids. And so that gives you a lot of other power that we don't currently have, which is these formulas to describe. And then we're going to talk about things like area of a pipe compared with velocity of the fluid and the ratio of fluid to velocity. So there's a lot of things to come up for fluids, for fluid dynamics. I'm going to try to give you some at-home little experiments you can do. I've got a couple demos for it. But yeah, this is a good start. Archimedes principle. I'm going to finish with that on here before I send this out to you. Archimedes principle, and then we'll talk about specific gravity next time as well. Pretty similar, actually. So before we talk about Archimedes principle, I'm sure you've heard the story of Archimedes. He was tasked with determining if the king's crown was in fact made out of pure gold, or if the person who made his crown in fact laced it with some other metals. So Archimedes developed an experiment to compare those things. Nowadays, it's even easier for us because we now have the metric system, which is completely based on water. If you think about it, we base 0 Celsius on the temperature that water freezes, 100 Celsius at the temperature water boils. We also base the milliliter and the conversion between milliliters and cubic centimeters on water. If you didn't know this, a cubic centimeter is equal to 1 milliliter of a fluid. So this is a linear conversion to a liquid or to a fluid measurement. So this is actually very powerful, right? Because if I were to take this container of water and I were to basically measure this out in a bunch of little cubic centimeters of cubes, I would then know how many milliliters I had as well. So it's a very it's an interesting conversion to make. And one more interesting thing is, this is an approximation, it's not always perfect, but it's 1 gram of water fits in 1 milliliter of space. Now if you're looking at this, which, based on this conversion I just gave you, 1 gram of water is in 1 cubic centimeter of space, which this is just the density of water. Okay, now it's not perfectly 1-to-1. I think maybe originally it was made 1-to-1, and then as we've gotten better with measurements, it's now closer. I think it's like 0.997, but 1's good enough for what we're doing. So 1-to-1 ratio. So if we have 1,000 grams, it'll fit in 1,000 cubic centimeters or 1,000 milliliters. So in some ways, you can use water to weigh things. If I didn't have this triple beam balance, if you were at home, you could take 2 cups, balance them perfectly, and then if you wanted to know how much something weighed in 1 cup, you would just add water using a beaker or a syringe, and you would know that the number of milliliters of water you put on one side, for every milliliter of water you're going to get, it's 1 gram, and then once your balance was even and flat and straight or level, you would know that the how much water you have is directly equal to how much weight you have on the other side, or mass. So that is a very useful idea. And this leads to the idea behind Archimedes' principle. Okay, if 1 gram per 1 centimeter. Okay, the idea is if I submerge an object like our cube that we found the density for earlier into a liquid, it should displace an amount of water equal to its volume. Meaning, I could answer the bottom part of this, and not only that, I will also know I can quickly find the mass. I waited earlier. So let's see if we can do this. Let's see how accurate this is. Here's my beaker of water. And I'm going, the scale doesn't matter. I just want you to be able to see it here. And actually, to make life a little easier, I will set it to track the beaker. Apparently the tracking software is not currently working, so I'm just going to balance it in the middle there. There we go. All right. So right now it's approximately at 100 milliliters. Going to add our cube of metal here. And I believe earlier when I did this, it almost went complete. It basically went exactly 25 milliliters. So it displaced, it went from 100 to 75, which is the backward side. So it went from 200 to 225. So basically 25 cubic centimeters. So 25 cubic centimeters is our volume of this cube. And if you remember, I estimated it at 27. So that means my measurement right here is probably a little bit off, or my measurement right here is probably a little off, or we can take both measurements and decide that it's probably closer to 26. Of course, I might want to use calipers instead of this. Calipers are a lot more accurate. And I might find that, in fact, it's probably closer to 27 because these things are kind of made perfectly to be 3 by 3 by 3. But 25 is a pretty good estimate just looking at this. If I had a beaker that had a lot more, if I had a beaker here that was a little easier to see that displacement, that'd be a little easier. So 25 cubic centimeters, and if I then get the mass of the cube again, which I believe I did before, but I don't remember what it is right now, so we'll do it again. And remember, this is what Archimedes did. Displacement, and then what he was able to do is he compared that to pieces of gold he actually submerged in water and weighed as well. And so he was able to make that conversion pretty directly. I'm going to look back up here so you can see what I'm doing. So 25 cubic centimeters. The weight, once again, is 271 grams. And that gives us 271 divided by 25 gives us 10.84. So we're a little closer to 11 now, so 10.84. So row 2. And so that is another method that we can use to find the density of an object. And this thing is meant to intentionally be a little confusing. It's made out of a mixture of metals. It's actually an alloy. So that's why I can't find these numbers on an exact chart. If I were to do the same thing with another metal, let's say this one is very light. Okay, you can't tell, but it's basically, feels like it weighs nothing. If I were to compare this one, let's put it down to maybe, well, at least less than 100 grams, so this is very, very light. It weighs less than 90, but more than 80. So it weighs about 87. So this one weighs about 87 grams. And it probably has the same volume. If I could hold them to each other, you can kind of see that they're exactly the same volume. But just in case, I'll submerge it as well. It goes up to 25. It's probably a little above 25, so it's probably 26 or 27. But we're going to get the same sort of results. 87 divided by 25, or 87 divided by 27. So 87 divided by 25 gives us about 3.48, and 87 divided by 27 gives us about 3.2. I'm going to look at the chart here. I'm actually going to bring you with me this time so you can kind of see the chart I'm looking at. So use my gimbal here that I got. Thing's very slow. There we go. All right. So we go to the top. We're sitting at about 3.2 is what I said. It says we're between bromine and barium. Grams between cubic centimeters. You see right here. Bromine and barium, 3.119, 3.59. Let's see if there's any metals specifically. Density of brass, density of metals. Well, we have aluminum here, 2.7. And I said we're about 3.22. I feel like it's probably aluminum, but we're a little low on the mass scale. One thing that we are forgetting, or that I am forgetting to add into here, is the fact that we have this little tiny hook on top. And so the hook might be throwing off the mass measurement because we're not actually considering the area, the volume, but it is being weighed, it is being submerged. So that could be one problem. So if I were to guess, that lighter one is probably aluminum. And it even looks aluminum. I'm sure if we did a scratch test or something like that, it's very lightweight and it's a shiny silver metal. Probably pretty close to pure aluminum, but this hook, if this hook's made out of brass, it's going to offset our weight quite a bit. And so I feel like that would be enough to set off the density, the difference between 3.11. Basically, that's the closest one we're going to find. Anyway, I'm going to let you go. I've been going on for way too long already on this video. I just wanted to give you sort of some assistance before you jump into the next set of work. Email me any questions. I'll quickly make a video answering any questions you have as well. Have a great day, and yeah, good luck. Mr. McLeod out.